Hello and welcome to this recorded learning module on Virtex-5 HDL coding techniques. This module is one of the recommended recorded learning modules for the Designing for Performance course and is also a part of the FPGA to ASIC REL curriculum. My name is Frank Nelson. I'll be your instructor for this module. I'm a Xilinx technical trainer and course developer. This module introduces some of the architectural differences of Virtex-5 and their impact on HDL coding techniques. This module introduces some of the primary concepts that impact the quality of results a designer will get when synthesizing for a Virtex-5 FPGA. This module also provides some detailed recommendations about creating effective HDL that will provide high speed and reduce the amount of FPGA resources used in your design. This slide describes the curriculum path for ASIC designers to learn Xilinx software, hardware, and FPGA design techniques. There are 5 RELs to help you get familiar with FPGA design. There's also a corresponding HDL coding techniques module for Spartan 3 devices. This content in this module will help you immediately start making coding improvements to your Virtex-5 FPGA design. There are 2 modules for Virtex-5 HDL coding techniques content. This is part 2. So if you have not heard part 1, be sure and take the time and go back and listen to it. For more information on these courses, visit support.xilinx.com and click on the education link at the top of the page. Also note that these RELs do not introduce the ISE design suite, good design practices, and other essential information. This content is part of our Fundamentals of FPGA Design and Designing for Performance courses. We recommend that you take the time to attend these courses. After completing this module, you will be able to build an efficient Virtex-5 design that runs at high speed. You will also be able to avoid the most common HDL coding mistakes that prevent Virtex-5 designers from achieving their performance objectives. Careful attention to the content included in this module is essential if you are new to designing for Virtex-5, and especially if you are handling the design conversion. We are going to discuss some of the most important ways to optimize your HDL code for a Virtex-5 device. After listening to this entire module, you should be able to make your own checklist of tips for building a high-speed Virtex-5 design. A common question is, how do I control how my synthesis tool infers clock enables? Recall that like synchronous resets, clock enables can be connected directly to the flip-flop or be connected to a LUT input. The intention is that you might want to design your lowest fan-out clock enables to use a LUT input. This will decrease the number of control sets in your design. To force the clock enable signal to be forced to a LUT input, you should code it as part of the register's output, as seen in the example on the right. So in this example, instead of coding it as we usually do, as what you see on the left, which forces the clock enable to the register's clock enable port, you should instead write the detailed equations and the explicit connections to the register's output. In this case, by having more than one input, it forces the clock enable input to the LUT input. Now, Xilinx is not recommending that you design asynchronously, just that you try to reduce designing low fan-out clock enable signals, that is, clock enables that drive fewer than 8 registers. Synthesis tools will get smarter about when to use the dedicated clock enable control signal port and when to move the clock enable function to the data path, but unfortunately it's going to take some time. You should also note that some synthesis tools allow the user to disable the use of a clock enable port on the register. Xilinx does not recommend this use, typically because on average it results in the use of up to 25% more lookup tables. So remember, to code for your low fan-out clock enables to drive the LUT inputs. This will enable the flip-flop to be part of a larger control set and give the tools more flexibility to meet your timing objectives, and you to have a better chance to make your high-performance design. We also want to mention that the map report, that is, the program that is part of the place and route or implementation process, can report on the number of control sets in your design. To do this, you'll have to run map with the -detail switch to get the analysis. Note that this report is long, but it may be useful, or you just may be curious. So don't forget that having a low number of members for each control set is cause for concern, because the tools may have trouble sharing slice and CLB resources with registers that are in those small groups. Now there is no typical range, but if I was attempting to do a design conversion, having some statistics would help me see the improvement I made during the design conversion. So this is just an FYI. If you want to see this kind of information, you can. As you know, gated clocks can cause glitches, increased clock delay, clock skew, and other undesirable effects. Using clock enables improves the timing characteristics and reliability of your design. Now there are several ways to use clock enable resources. To gate entire clock domains for power reduction, it is preferable to use the clock-enabled global buffer resource called the BuffGCE. This is the symbol here taken from the Xilinx Unified Libraries Guide. This will deactivate the clock being distributed on a global basis. As an FYI, don't forget that Virtex-5 supports asynchronous switching of individual clock domains with the BuffGMux primitive. For applications that only attempt to pause the clock for a few cycles on small areas of the design, the preferred method is to use the clock-enabled port of each FPGA register. So try to take advantage of the BuffGCE or BuffGClockEnables functionality. It will save you from having to route a high fan-out clock enable throughout your device, and saving routing resources can do a lot to improve the speed of your FPGA design. We discuss synchronous design techniques and efficient ways to build clocks in the Fundamentals of FPGA Design course. Many signal processing algorithms perform an arithmetic operation on an input stream of samples, followed by a summation of all outputs of the arithmetic operation. To implement this summation in an FPGA, the adder tree structure is typically used. One of the key difficulties with adder trees is its varying size. The number of adders depends on the number of inputs to the adder tree. The more inputs, the more adders that are needed, and this increases both the amount of resources and the power consumption. Larger trees also mean larger adders in the last stages, which can negatively impact the speed. It is simply better to implement these with dedicated resources such as the DSP Slice. This implementation involves the computing of the summation incrementally using chained adders instead of adder trees. This maximizes performance and lowers power for DSP algorithms because both logic and interconnect are contained within the dedicated silicon. When pipelined, the performance is approximately 500 MHz in the fastest speed grade, independent of the number of adders. To learn more about the process of converting a direct form filter to a transposed or systolic form is detailed in User Guide 73, Extreme DSP for Virtex-4 FPGA's User Guide. Likewise, you should check out User Guide 193, the Virtex-5 FPGA Extreme DSP Design Considerations document. When inferring dual-port block memories, it is possible for both ports to access the same location at the same time. In this case, the contents cannot be guaranteed. The latest FPGAs have 3 programmable operating modes to govern the memory output while a write operation is occurring. They include write first or transparent mode, read first or read before write mode, and no change mode. Synthesis tools can infer these configurations based on your HDL coding style. You should avoid read before write mode to achieve maximum block RAM performance, however. Synthesis tools such as Simplify insert bypass logic around the RAM to prevent the possible mismatch between the RTL and the hardware behavior. This extra logic is intended to force the RAM outputs to some known values when collisions can occur. If the designer knows that these collisions cannot occur in his system, the synthesis tool settings can be used to prevent bypass logic from being added to the application. This extra logic has a negative impact on the memory performance and is therefore recommended that you prevent its addition.